Ya voy a empezar. Hi, we are Sania Gonzalez Telles and Maria Jose Chaboya Zamora, and we are going to present Michelson interferometer. This is the outline of our report. The objective is to analyze interference of light and microwaves using a Michelson interferometer, and the specific goals are to obtain an experimental value of the wavelength for light and microwaves using different methods, and compare the methods between them and the result obtained with the manufacturer manuals. In with the introduction, first we're going to talk about electromagnetic waves. Using Maxwell laws, we can derive equations for the magnetic and electric fields, which are presented here in equation 1 and 2, where this is the expression for the speed of light. Now, if we consider a plane wave that is propagating in vacuum in the positive x direction, we're going to obtain, also using Gauss law, that the electric field related to this wave, it's going to be perpendicular to the propagating direction, and we're going to say it only has components in the y-axis. Now, from Faraday's law, we can obtain this equation. This equation is very important because it also tells us that not only the electric field is perpendicular to the propagating direction of the wave, but also the magnetic field is perpendicular to this propagation. Now we can write our wave as an harmonic wave, as we saw here in equation 5, and using this equation 4, we can substitute, and integrating, we're going to obtain the magnetic density flux density, and we will obtain this equation. Now we can see that this part of here is the same part of here, so we can rearrange, and it is evident that in vacuum we are going to obtain that the electric field and the magnetic field only differ by a scalar. This tells us that the waves, these two waves are in phase, and we also obtain that these waves are perpendicular, and that the cross product is going to give us the propagating direction of the electromagnetic wave. This is important because before it was thought that electromagnetic waves didn't propagate in vacuum, but the Michelson interferometer proved that this was not true.
Now we're going to see how a Michelson interferometer works. It produces interference between two beams of light by splitting a light beam into two parts and then recombining them after they have traveled different optical paths. A light source emits a light beam that strikes the beam splitter O, where we can see in the both figures, where half is reflected until it reaches the mirror M2 and half passes through the mirror to reach the movable mirror M1. The two waves are reflected by their mirrors and return to the beam splitter and then towards the detector D. Therefore, the waves are united and they interfere. From the figure, we can notice that one of the beams passes through O 3 times, whereas the other beam only passes through it once. And to ensure that both beams transverse the same thickness of glass, we position a compensator plate C of transparent glass parallel to the beam splitter O between the movable mirror M2 and the beam splitter. With the compensator in place, we can say that any optical path difference that arises is actually from the path difference, and it negates the effect of dispersion. As we can see from equation 8, that is the equation giving us the path difference, and we can suppose that the path difference is a integer number of the wavelength m lambda. That the constructive interference occurs when a bright image at a point on the source is seen at detector D. Now the light from any other point on the source whose two beams have the same path difference then undergoes constructive interference and produces a bright image, as we can see in the detector. The collection of these points images a bright fringe corresponding to a path difference m lambda. When M2 is moved by a distance of half the wavelength, the path difference changes by 1 wavelength. and each fringe moves to the position previously occupied by the adjacent fringe. Consequently, by counting the numbers of the fringes and passing by a reference point, we can measure the distance displacements as shown in the relationship in the following in the equation 9. Then we have the materials and equipments that were used for both light and the microwave interferometer. To perform this experiment, we use the Pascal precision interferometer arranged in the Michelson interferometer mode, where we will observe the interference pattern produced by the superposition of these waves. And once the interference pattern was obtained, it was possible to move the movable mirror, and the different distances traveled by it were recorded, as well as the number of stripes that passed through a fixed point on the screen. And for the microwave interference, the experiment consists in changing gradually the position of one of the reflectors until it reaches 10 maximums that have been transversed according to the to the meter reading. Then the distance that reflector was moved was recorded, and the procedure was repeated multiple times.
We're going to begin with the analysis for Michelson interferometer for light. As we see in the theory, the equation that gives us a relation between the distance traveled by the mirror and the number of stripes passed through a specific point is this equation. For this experiment, we recorded different values for the distance traveled by the mirror and the number of stripes that pass during this travel. Now we can plot this distance traveled by the mirror as a function of n, the number of stripes passed, and use a linear adjustment given by equation 11, where the slope of this equation is going to be given by equation 12. Now, doing this linear adjustment, we are going to obtain the slope that is going to be 0.032 with an error of 0.01. Here is our plot. Here are the points of the data and our linear adjustment. And using the value of the slope A that we saw was lambda divided by 2, we were able to obtain the value of the wavelength that in this case was 0.64 micrometers. We compared the result with the real one given by the manufacturer manuals and obtained an error of 1.5%.
Now for the experiment using microwaves, we used 3 different methods. In the first method, we measured the values of the position of the movable mirror, the number of the maximum transfers, and the distance traveled by the reflector, as we can see in the table. We then calculated the average and measured the distance, considering n to be equal to 10, and we obtained the wavelength, as we can see by equation 13, with a value of 2.76 plus minus 0.08 centimeters. And we calculated the associated error using equation 14. For the second method, we use the same data from the first method, and we determined different values of lambda for the different values of the distance traveled every 10 maximums, as we can see in the following table. We then calculated an average of the wavelength and obtained a value of 2.78 plus minus 0.09 centimeters. For the last method, we did a graphical analysis using the following table, and we plotted the position of the mirror as a function of the number of stripes, as we can see in the graph. And we used a linear approximation to obtain the wavelength through the slope, as we can see in equation 17, which gave us a value of 2.76 plus minus 0.04 centimeters, and we obtained the associated error with equation 12. In the following table, as we can see, we have presented the obtained values and their comparison with the theoretical value, and we can see each of the wavelengths obtained the same value, with all of them having a percentage error of 3.2. And then we answered the question from the manufacturer's manual. Why would an optical interferometer using visible light rather than microwaves provide better resolution when measuring distance than a microwave interferometer? Well, it's possible to obtain the distance traveled by the reflector by using the equation for distance, which is the distance equals m lambda divided by 2. An optical interferometer using visible light would provide a better resolution because the wavelength of the laser is much smaller than the wavelength of a microwave beam, which allows us to make smaller and more precise measurements.
In the first experiment, we observed that the data obtained was not greatly dispersed and had a strong correlation. This allowed us to obtain an acceptable result, which is similar to the one given by the manufacturer manual. And also taking into account that the wavelength of a red laser can be between 630 nanometers and 670 nanometers, we conclude that our result is within the ranges. And we believe it is possible to get a better result if we record more measurements. Now, for the microwaves interferometer, we saw that the three methods used give us the same wavelength, with only the difference being the error associated to each value. We believe the best method is the graphical method because the associated error was lower.
Now for our conclusion, in the microwave interferometer, using light, we successfully obtained the experimental value of the wavelength with a value of 0.64 plus minus 0.02, and with only an error percentage of 1.5. For the microwaves, we used the three methods, each of them giving us a value of 2.76, which each their own different error associated, but each method had an error percentage of 3.2%, and therefore we concluded the best method was method 3 because it gave us a smaller uncertainty. And then we present the reference use for this report. Thank you.